on that. So without further ado, let us get to work. Right. Okay. So the opening question is, how do we know that one process impacts another? How do you know that to increase sales, you need to hire more people? Maybe to increase sales, you don't need to hire more people. Quite the opposite. You need to fire people and increase the quality of those workers. Yeah, sounds completely counterintuitive. Like, why should I fire people if I want more sales? Well, if you fire people, you can pay them more, they will try harder, you will have greater sales. Okay, so with regression analysis, with econometric modeling, what we're trying to do is we're trying to find what variables, what processes impact the process which we are interested in. This module, this presentation is presented on the basis of a linear regression. So basically what we're saying is that the relationship between two variables, this one and this one, whatever these are, basically we're assuming that if we graph a relationship between these two variables, this relationship is best described by a straight line. And right away, now obviously this line is a better representation, but with regression analysis, just like with all the other tools in management, we have to find a balance between easy to use and complicated. We don't easy to use and reliable, not complicated, because there's no point of creating a regression, an equation that explains this wave to us if we cannot use it. Okay, straight line y equals b plus ax is a simple equation which you have seen in high school and probably in college as well. Okay, so this method of estimating a straight line is called ordinary least. One of the methods is ordinary least squares, or simply OLS. Again, OLS is not the most advanced method, but due to its robustness, which means its resilience to problems, and the possibility of modification, it is probably the most widely used method in econometric modeling, definitely in consulting. I can tell you right away. And probably, again, I've done in consulting over 40 projects. Maybe in 2-3 we used something different than OLS. So very, very common. By the term econometric modeling, we should understand the estimation of model parameters. Okay, but more on that in a second. Before we go further, it's important to ask why we model anything at all. Well, the first reason is to build a model that will allow us to use identified historical dependencies. So, for example, we can value a house. If your house has 4 bedrooms, 2 bathrooms, and a jacuzzi, with an econometric model based on past houses I sold, I can tell you what will the price of this house be. We simply can price a company, we can price a car, we can find the probability of somebody being sick, we can find the probability of some cure working, and so on and so on. And the second reason of modeling is the attempt to forecast future values. We'll talk about that. Down the road. So in linear model equation, this guy right here, we have y is a dependent variable because its value depends on the right-hand side of the equation. Okay, so y is the dependent variable. It is modeled, or its value depends on x's, which are independent variables, also called explanatory variables because they explain y. Beta 0 is a constant, and this is the error term. Okay? So this is an equation of our model. After the model is estimated, we add the hats to it. Okay? And therefore, here we have these estimates. So these are parameters. Okay? The coefficients become parameters. So if x1 increases by 1 unit, y increases by beta 1 unit. So at this point, our error changes name to residuals. And entire econometric modeling is about residuals. Everything. Everything is about these dudes and dudettes. Okay? Let's take a look at a graph over here. These blue dots are our actual values, our y. Okay? We fit a regression, a straight line, green line. Okay? And here, so here is what the actual value is, and here is what our model predicted. Difference between these twos are called residuals. That's the difference.
Sorry. What is the blue dots? What is that?
Actual data.
Actual data. Okay, thank you.
No problem. Ask any questions you might have. Okay. So when we will get such an equation, this will be a number, this will be a number, this will be a number, and then we plug in values of x's, and we get the value of y. And the difference between the actual value and our value, our estimated value, is called the residual. Okay? Now again, ideally, we would like for all of the for our model to be as close to the blue dots blue dots as possible. And therefore, the goal of the ordinary least squares is to minimize the value of sum of the squares of residuals. So basically, OLS takes this distance, squares it, adds all of these distances, and it fits such a line. So whether it's going to be this line, or whether it's going to be this line, or whether it's going to be this line, it fits such a line that minimizes the distances. Therefore, basically what we're looking for is we're looking for a line of a best fit, which means a line that best fits our data. Phrased differently, a line which best represents our data. Okay. Now the residuals of the model, and again, please remember, econometrics is all about residuals, need to be a random element. Because look, let's go back over here. If I'm saying that my y depends only on x1 and x2, then what I'm saying is that this part of the model explains my residuals, my y. So if y is sales, this is number of persons we have working for us, and this is, I don't know, number of stores, then what I'm saying is number of sales depends only on number of persons working and on the number of stores. Nothing else matters. That's why it's a closed, think of it as a closed box. Okay? Therefore, everything else that remains that still impacts my sales needs to be random occurrence. something that I couldn't possibly predict. Okay, so in other words, this value, this residual, this distance over here that I cannot predict or cannot explain with my model must be a coincidence. For some, for some reason, something happened. For example, you manage a restaurant and your sales are on a normal level, and suddenly a tour bus with a bunch of tourists shows up and they suddenly increase your sales. There's no way in an econometric model you can account for a bus of tourists to actually stop at your restaurant. Okay, coincidence. Okay, something we cannot explain in the model. And this leads me to another thing about econometric modeling, that in econometric modeling we are not modeling instances, individual examples, we are modeling long-term trends. Okay, so if we go back over here, we're not modeling this guy or 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 this guy. We are modeling a long-term relationship. Okay, and again, this is something that some people sometimes get confused about econometric modeling. Sorry, because they're like, oh, well, one day my sales were here, but your model said here, so your model sucks. No, because the model shows a general long-term relationship between these two variables. Okay, and the reason why I highlight this is for you to understand that econometric models are very powerful tools. However, at the same time, you have to understand what are their limitations. So again, econometric models represent long-term stable relationships. Econometric models do not represent individual instances. Okay. Now, when we are talking about basic requirements of oh, I see there's a mistake over here. Sorry. There we go. If we're talking about the basic requirements of econometric models, is that they need to be blue, just like the color or name of a fantastic Australian cartoon, although it's called Bluey. The word blue is an abbreviation for best linear unbiased estimator. Best means that the estimated coefficient has the lowest possible variance. Notice, blue one has a small variance. Red one has a very large variance. Green one also has a very large variance. So from these three, the blue one has the smallest variance, distance between these 2 points. Therefore, it is best. Linear refers to the fact that the relationship between two variables is best described as a straight line. Unbiased means that the estimates of our model are distributed around the true value of our coefficients. Okay, because we are estimating this guy over here, we're estimating the slope beta. Okay, because we don't know its true value. If we knew the true value, we wouldn't need to estimate it. So from all these three, red one is biased because it's distributed around some other variable while green and blue are both unbiased. So for this picture, I have written, the blue is unbiased, small variance, green is unbiased but large variance, red is biased and is a large variance. Okay, so for example, one of the first questions that you should ask is, as a manager, is okay, so let's say I come to you, okay, with a solution, here's an econometric model, blah blah blah, this is what it says, and you should ask, hey, are the results blue? Okay, very first question. Look how simple this question is. It means whether it's best, linear, and unbiased. But this is the very basic element. So when I train, for example, managers about how to, what questions to ask and how to read econometric models, this is when the analysis was done using OLS, this is the first question I tell them to ask. Is it blue? If it is, how was it? How do you know? And then based on the answers to that question, they're able to understand whether they're buying a good product or whether they're buying a bad product. So another thing is that the values of the estimated coefficients, our betas, should not change significantly as variables are added or subtracted from the model and due to the sample size or due to the sample. Okay, so it cannot be a situation that we draw a random sample from our customers and we find some econometric relationships within that sample, and we draw another sample and we find different econometric relationships. Okay, it cannot work like that, because if depending on a sample we get different results. So for example, in sample number one, our marketing strategy works, but in sample number two our marketing strategy does not work, then if you're a head of marketing, should you continue the strategy or should you not? Okay, that's why we say that basically what the sentence says is that results of your econometric models should be very stable, and therefore they should not vary depending on a sample. Okay, so the second question you should ask is, how stable are the obtained results? Okay, now I gave you an example of a marketing strategy, and this is a real life example where we came in, my team and I, we came in and we had to clean up after a previous consulting firm, because now he's my friend. The marketing director called and he said, long story short, again, I have two samples done by the same company. One says our marketing strategy works, the other one says our marketing strategy does not work. Mr. Thomas, what should we do? Okay, that was his question. And the problem was obtained results were not stable. So what we're looking for consistency. Okay, again, real results cannot depend on the sample you take. Again, sorry for continuing to drinking, but it's a lot of medicine. All right. So more formally, we should act according to the following assumptions. Now, as managers, you can of course ask about them, but this is generally something that either you would hire an outside reviewer, maybe like me, to help you with this, or you have somebody on your team. So again, linearity of parameters. If your estimator is blue, L is linear, you have this. Random sample, if you're doing a study based on a sample that represents a population that I told you, I think, during the very first class, you should have a random sample. Okay, easy to do. Explanatory variables are not constant, and there is no perfect linearity between them. Let me translate that into English. So the problem is, if you have y and x, and it looks like this. X is only one value. Well, no. We need different axes to give you different y's. Okay? The expected value of residuals is 0, which means you include in the model all possible x's that impact the variable you're interested in. So if you're interested in sales, your model should include all the variables that impact sales. Okay, you cannot omit, we aim not to omit anything. Okay, and that's very crucial. If you don't meet this fourth requirement, you have something called an omitted variable bias. I'll give you an example. Again, real life example, and that's why I don't tell you the names of the companies. To do this, we need to exit because it's going to be much easier for me to explain in Word. Blank. Okay, so the job was to predict sales, okay, as a function of whatever, and this whatever, this question mark, represents all processes that impact sales, okay, with a very strong emphasis on all processes that impact sales. Unfortunately, the consulting firm that this company hired did this. Sales are equal to constant plus the first coefficient, assets of the company plus, plus the residual. Okay, and I was a reviewer on this case, and I said, whoa, so you're telling me that sales of this company are dependent on the assets of this company? What about number of employees? What about the number of stores? What about whether we have an ongoing marketing campaign or not? What about training of our employees? What about any sales? What about any sales, as in promotions, discounts that we're having? What about all the other elements? Okay, and this is the problem when your model is underspecified. So you, as a manager, when it comes to using econometric models, you need to ask a question: are all the processes that impact sales, for example, included in this model? Okay.
Sorry.
What's up? Yeah.
Can you please show one more time this formula
Word?
that you?
You mean the Word document?
Yeah. Mm-hmm.
Of course. Yeah. There we go.
And how we have to calculate all of this? You said that like we should mention all the processes possible, like so for example, ongoing campaigns and so on, and
yes,
how we should like calculate it or add to the formula.
Okay, so the equation of the model will be constant plus beta 1, and would, for example, have a number of workers, okay, plus beta 2, we would have number of stores, plus beta 3, and so on and so on. And we extend it to include all the processes that impact, well, in this case, sales, but it can be whatever it is whatever the process that you have, that you're interested in. Because this one over here, I'll highlight this in red, it had something, this had a problem of omitted variable bias, which means there are processes, variables, or omitted process bias, which you should have in the model, but you don't. Usually that is a result of laziness, to be quite honest. When I was a reviewer on this case and I asked the consulting firm, and I'm using the words consulting firm very loosely over here, because they couldn't consult a dog on how to eat the bone, or anything like that. Basically, they said, "Oh, yeah, we didn't think it was important." And when the manager heard this, like the manager's like, "Hold on a second, you're telling me the number of stores I have don't impact the sales I have, and you're telling me that whether we have marketing promotion does not impact sales, or so on." So where are you getting this from? And basically, they, long story short, they basically said, that they didn't feel like doing it.
I see.
Yeah, right. So come on. This why again. This is in this class again. I'm not teaching you how to do this, but I'm teaching you how to understand this, how to ask questions, and so on. Okay.
Yeah, I see. So let's E. It is like an this one I forgot. Oh, what is
It's called the residual. It's the rest. It's the rest. So if you have all the things in your model, that excellent question you asked. If you have all the things in your model, then what you're saying is, okay, all of this determines sales. Well, if all of this determines sales, then this should be 0, right? If all of this in green impacts sales, then this is not existing. It should be 0, because you're able to perfectly explain your sales. Okay. However, if you have this omitted variable or process bias, then this is going to be very, very large. And this does not explain anything. You just don't see it. Okay. So that's why, again, we're trying not to have this omitted variable bias.
Okay, thank you.
No problem. Ask any questions. It's better you ask me questions now than you have to pay for it. That you have to pay for it later. And I'm not talking on the exam. If we meet the first 4 requirements, our estimator is unbiased. So we have this U from blue. Okay. Additional if we meet assumptions 1 through 5, the estimator is blue. Sorry. Hold on. Sorry. Oh. There we go. So if we meet assumptions 1 through 5, then our estimator is blue. So you already know what questions to ask. Hey, did you include all the processes in the model? Yes. Okay. Why did you select these processes, not other processes? Why did you select number of stores and not the number of employees? And then ask questions 1 through 5. Okay. And if it meets this requirement, then it is blue. Now, almost any model will work. That is, for most sets of variables, it is possible to estimate a model. Okay. Unfortunately, and I don't want you to fall into this. Don't want you to fall into this path, but unfortunately, a lot of both consultants and managers fall into this notion that if Excel or Gretel or eViews or Stata or SPSS or whatever else software you have gives you, if it gives you, why did I not change it? If it gives you some results, in the sense that it gives you a number as a result of whatever it is that you're trying to do, then this number is correct. Mathematically, this number is correct. But the question is, how reliable is your result? Again, going back, how reliable is a process that explains sales in your company that does not include the number of workers or number of stores you have? Not very reliable. Okay. Next, will the model work in every situation, or only in the one situation where it works by chance? Again, a model is let's call it an average of a long-term relationship between number of workers and sales, for example, number of stores and sales, having a marketing campaign and sales. Okay, so we wanted to show and fit the long-term relationship, not work one time by chance. Okay, that is very bad. To be able to answer these two questions, it is necessary to test the assumptions, assess the quality of the model, and only at the very end evaluate the estimated relationships. So what I'm trying to push on you here is that you, whenever you use the results of an econometric model as managers, you have to ask the source of that model, internal, external, whatever to the company can be. But have you tested the model, and what are the results of the test? Because if you have not tested the model, then reliability of that model is equal to 0. Yes, what's up?
Sorry, what is OLS? I just skipped a bit.
Ordinary squares. Ordinary squares is this method of calculating the model.
I see. It's this one blue, or it's not? No. Like
no, OLS is just a mathematical formula. And for the and blue is the quality of the mathematical formula. So you want your OLS model to be blue.
I see. Okay, thank you.
So the model which you have estimated using OLS, you want the results to be blue. Okay.
Yeah, I see. Thank you.
Yeah, go ahead.
So OLS is so this is a method of calculating. Yeah.
Absolutely. Yeah.
Okay.
Exactly.
Thank you.
Sure. Yeah. Ask questions if you have. So additionally, now there are many tests available, for example, in the Gretel program, and so on and so on. Is it worth using all of them? In theory, yes, of course, because the more tests you have, the more reliable, the more sure you are that the solution you have is the correct solution. The analogy I give here is, imagine you're going to a doctor and the doctor says, "What's up?" And you say, "I don't feel well." Well, that's test number 1. And then the doctor writes you a prescription just based on the "I do not feel well." How reliable is the diagnosis? Not very. However, if they check your pulse, they check your blood pressure, they check your temperature, they check inside your ears, inside your nose, they check your eyes, they check, your lungs, and so on, and then they come up with a diagnosis. Now that's a reliable diagnosis. Why? Because they have ran many checks. Okay, so similarly with econometric models, the more tests we do, the more reliable are the results, and this is what we should strive for. Now, sometimes in the quote unquote in the real world, you will run into and again, I'm using the word consultants very loosely here, who will tell you, oh yeah, this is a textbook approach, blah blah, in real life we don't do this, we just go with it. The answer is no. The answer is econometric models should work the same in real life and in textbooks. Okay, now textbooks will very often have very idealistic test results versus in real life there will be very realistic, but it doesn't matter. They have to pass all the tests. Okay, so again, I say in theory, yes, you should do all the tests, all in quotation marks. However, in practice, it's not necessary. Again, just follow the principle. The more tests we perform, the more confident we can be in obtained results. Okay, and I very often leave it to the managers. I say, well, when I was doing the econometric analysis consulting, I would do all the tests possible because I want to be sure of my work, because at the end of the day, it's my name on the analysis. Okay, and you only have one name. Of course, you can change it, but you get the idea. However, when I trained managers, I said, listen, if it's a stupid, simple little thing, okay, go ahead, don't test. It's up to you how much confidence you want to have in the results, and I leave it at that. Now, note, testing of the model has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 tests, 2 evaluation criteria, which gives us 14, and only then do we come to the discussion of estimated coefficients. Only then do we come to the discussion of obtained results. Okay, and now, because consultants get paid for this, they don't get paid for this. 1, 2, 3, they don't get paid for this. We get paid for unethical consultants will try to skip over these 1, 2, 3 parts. And now it is on you as managers to ask questions. Was the model tested before the estimation? Was the model tested after the estimation? What is the degree or quality of models fit to the data? Okay, and you can use this presentation. I'll be very honest with you. This is the presentation that I used very often when I taught managers. So I thought it fits, since you guys are in management and girls are in management. It would fit you. So sometimes I make corrections because not everything got translated perfectly. So first assumption is that the dependent variable, which is our y, is something we call a continuous variable. Okay, so the dependent variable can take any value. In other words, it's not artificially limited. So your height, your weight, your GDP, inflation can be as big or as small as possible. If somebody comes in and they are 3 meters tall, okay, can be. Okay, if somebody comes in weighing 500 kilograms, very unlikely, but sure. Okay, the inflation is 400%. I'm sorry if that's in your country, but yes, that's acceptable. What we don't want is we don't want variables like yes, no, or very bad, bad, neutral, good, very good, and things like that. So for this to work, it needs to be a continuous variable. Sales is a continuous variable, but whether a consumer bought or not is a 0-1 variable, a so-called dummy variable, or so-called dichotomous variables, and there are different models. There are different models for that. Okay, so also, so here, if we're sticking with the sales, it's one of the last projects I did, so that's why the sales is stuck in my head. So if we're speaking about sales, like when I was talking to the customer said, listen, I'd like to know whether a customer purchases or not. And I said, listen, okay, not a problem, but it's a completely different thing than the amount of sales you have. Okay, sounds like similar, but because it's consumer buying something or not, but it's a completely different. It's a completely different. It's a completely different element. The second requirement is that the relationship between the dependent variable and the independent variables, as they appear in the model, must be linear. So let me skip over here. Here we in panel A, we see that this relationship is not linear, right? It's a curve because it's y versus x. However, if we square x, now it's a linear relationship. Okay. Similarly, over here and down here in panel A, the relation between y and x is a logarithmic relationship. It's not a straight line, right? It's the inverse kind of this, because logarithm is the inverse of that. However, if we again transform the variable into logarithms, it's a linear relationship. So remember that we're trying to, doesn't matter if in your model you have x or you have x squared or logarithm of x, what you're trying to do is you're trying to have a linear relationship. Let me explain why. Because let's assume that your data looks like this. Okay, so here you have y, and here you have x. And your data looks like this. Okay, and to this, you try to fit a straight line. Well, is it going to be like this? Is it going to be like this? Is it going to be like this? Or maybe it's going to be like this? Okay, you cannot fit a straight line. And again, another problem that we have is that when you have this type of data and you try to fit a straight line. A different example, again with sales, I'll do it over here, is when data is like this. Sorry, takes a second. Notice, what do we have here? We have a wave. We have something called seasonality. Okay, sales are high, they drop, then we have very low sales during the summer, very high sales because around Christmas, end of New Year's, summer, Christmas, New Year's, and so on. If you're trying to fit a straight line over here, look what's happening. You are either overvaluing or undervaluing your data. However, if you would introduce this as a sinusoid, you'd be completely fine. Okay, so the requirement again we're talking about is the relation between y and x as they appear in the model has to be linear. Okay? Now, stationarity. When it comes to stationarity, basically, the problem of stationarity is that when you have time series data, which we talked about this type of data all the way in lecture number 1, which is, again, for example, let's say the blue line represents sales for simplicity. Okay, so blue line represents sales. Well, if we next to sales use a different color, if next to sales we put in number of workers, note they both have a positive trend. This one's increasing, and the green line is also increasing. The problem is that if you have both variables which have a very strong trend, and you explain one with another, you run the risk of something called a spurious regression. So it's a regression where, again, the software that you're using is going to give you numbers, but these numbers are unreliable. Okay, and I'll give you a macroeconomic example. Notice over here, blue line, sorry, blue line represents, should be GDP, sorry. Blue line represents GDP, gross domestic product. Red line represents physical capital. Okay, now these two are non-stationary. Okay, and therefore if we would run this regression, or we say that it's GDP. GDP is a function of physical capital only. We would get I guarantee you, we would get a fantastic model. Really, really fantastic model. Problem is that model would be what we'll call unreliable. It would be spurious regression. Because again, when you have two variables that have a very strong trend, then obviously when this one is growing, this one is growing. So you can come up with any type of a relationship between the two, and it will be correct. So let's say this is A, and this is B. Okay? Now, if I would ask you, which does A impact B, or does B impact A? From this, you cannot say. Because when B is increasing, so is A, and when A is increasing, so is B. So we run here into the same problem that we run in when we talk about when we talked about correlation. Okay, that when you have in correlation, we say correlation is not causation. So based on correlation analysis, which we did, I think, last week or 2 weeks ago, you cannot talk about the impact, about the causal relationship. Same thing over here. If your data is not stationary, then you cannot talk about impact. But which is a very big problem, because in econometric analysis, impact is what we're all about. So when this is again very, very specific to time series data. and therefore, for example, when you'll be working as managers, doesn't matter in basically what business, I guarantee you'll be working with data plotted against time. Do not let trends deceive you, and therefore do not let yourself be confused or deceived by existence of spurious relationships. In other words, fake relationships. And fake is in quotation marks because there is a relationship over here, but we don't know if really changes in B impact A. Any type of analysis that we have has a problem of outliers. Okay, for example, we did probability distributions. Well, if here's our average, okay, then normal distribution around this average would look something like this. But if we have an observation over here, this distribution is going to look like this.
Sorry.
Yeah.
Can you please go back to
Here?
slide? Here? This one. And can you please repeat what is this formula for? Why do we need it?
Oh, this formula is describing us this relationship over here, where GDP, which is the blue line, is explained with physical capital, which is the red line. And the problem is that in this case, we have two very strong positive trends, and therefore, when you have two variables that both have a positive trend, that both have very strong trends, one can be positive, negative, doesn't matter. But when you're dealing with two variables that both have very strong trends, what that does is that actually how should I say this? In other words, distorts your observations because you're actually explaining one trend with another trend, not one process with another process, if that makes sense.
I see.
Okay. If not,
yeah, and what is this one? PKBT? How it spells?
GDP. It's GDP. Sorry,
GDP.
GDP should be GDP. Sorry about that.
Okay. Thank you.
Oh, sorry. No problem. Okay, so back to our outliers. The problem with outliers is that outliers distort our observation. Let's say we have, and again, let's go to Word because typing in Word is easier. Let's assume we have these numbers. Okay, and we are asked to calculate an average from those, again with a headache. So it's 3, so I'm using 4 plus 6 plus 3 plus 6 gives us 22 divided by 5. No, sorry. 22 divided by 5 gives us the average. So the average we get over here is 4.4. Now let us copy the same numbers, but introduce an outlier. Okay, so we have 1022 divided now by 6. Okay, do you see how, hopefully now you see how presence of an outlier impacts the results. Here, if I would ask you, hey, what is the average amount of, I don't know, average amount of kilometers you run in a week, well, the average for these people is 4.4 kilometers. However, if we introduce some super runner and ask you, hey, what is the average number of kilometers you run in a week? It's 170. Therefore, what the hell? Therefore, we in any type of analysis, we do not allow outliers. I know it's a statistical joke, but I don't know how much money you have, but I bet you if Elon Musk would join our class, then on average all of us would be billionaires. Okay, but that's Elon Musk. But when Elon Musk leaves, on average we're not billionaires, and that is the presence of an outlier. Therefore, when we're doing our analysis, we're trying to get rid of those outliers, those extreme values, because they distort our observation. In a simple econometric model, notice over here. Here we have this guy over here, and this is the outlier. Now, and this produces this equation. So y is equal to 1.3 times x plus 10. If we remove that outlier, now we're in panel B, notice that we get a different result. It's not the relationship is not 1.3, but 1.9. The constant is not 10, but 1.5. Therefore, we don't like outliers, because outliers pull our analysis towards themselves. And we saw the same thing with our example of kilometers being ran every week. If we have an outlier, does not matter what we are calculating, that outlier is going to if it's a positive outlier, as in it's a very large number, it's going to increase whatever we're calculating. If it's a very low number, it's going to decrease whatever the heck we are calculating. Therefore, for example, when we analyze the performance of our stores, and we have one store that is just super, like the sales are extremely large, there's a very good argument that we should remove that store from our analysis, because it's going to distort our observations. And I'm skipping slides just because again the aim is to give you an idea, but I wanted to give you a full presentation, so if needed you can go back onto this presentation, and if you have any questions you can talk to me. Oh, I forgot, or if I mentioned this earlier, I'm sorry, but I have set up consultation hours for this class and another class I teach. So these you do not have to attend. They are not mandatory or obligatory. However, if you have a question, you are, for example, about something we talk about in class, feel free to simply join into the meeting, because I'm sitting in a meeting waiting for students. And then you can talk to me. You can talk to me live on Teams. But again, it is not mandatory. So there are 4 hours like that set up in December, and 2 hours like that in January. Okay, so just a note on that. Okay, now. So we have, let's say we have an outlier like that. What is the solution? Well, the simplest solution to the problem of outliers is simply to remove them. But what if this outlier is really part of the thing we're studying? What if this outlier is not one, but there's 10 of them? What if we draw one sample, we saw an outlier, we draw another sample, we we see an outlier, we see the next sample, we draw a next sample and we see an outlier. Okay, well, can we remove them? Well, let's start with the fact that the removal of any observations should be described and justified. Okay, and here we move to another question that you should ask an analyst. Have you removed any observations? If the analyst has removed any of the observations, it is your job as a manager to ask which observations you have removed and why have you removed them. Okay. Hold on a second. Sorry. Okay. Sorry. Okay, I'm back. I'm sorry. My daughter came back from school, so hugs and kisses. Hopefully you'll forgive me. So going back to this. Now,
yeah, of course, don't worry.
Thanks. So, for example, you cannot remove observations to improve the model or to improve your analysis. So, over here, I said I removed this to illustrate the point, but in reality, first thing I would like to do is try to explain why is this observation over here while everything else is down here. Like, where the heck did this come from? And the reason one of the reasons why I say we should explain it is because the most often source of outliers is an error in data entry. So this, instead of 30, this should be 3. Okay, and then it fits this line. Then it fits this line quite nicely. Therefore, again, as managers, what you should do is, again, if you removed something, that's fine. I'm not telling you that that is an incorrect thing to do. I'm simply asking you why. Because such a procedure will lead to a situation in which the model will, for example, test well, but its results have nothing or very little to do with reality. Because if you have selected a sample of observations and the sample goes like this, and you start removing observations, and suddenly your sample looks like this, well, this represents reality, this doesn't. Okay, so it's A, B, C, A, B, C. The problem is, again, when you remove observations, okay, when you remove observations, you change the composition of the sample. You change the composition, you change what the data represents. Okay, so if here we have the real world, well, we collect data to represent the real world. Then this data goes into some analysis, and we hope that this analysis represents the real world, right? So it looks like this. Problem is, when, again, econometric modeling, anything else, once you start removing data, okay, then this data no longer represents the real world. When this data does not represent the real world, then the analysis that uses this data cannot represent the real world. So this analysis will represent this data very nicely, but that's it. You lost the connection with the real. You lost the connection with the real world. And again, if you're sure that this is only one outlier like that, sure, remove it. Explain it. Hey, I found one outlier. I tried to explain it. I can. I tried to look for another one. I didn't find it. So that's it. Okay? And that's completely fine. However, problem is that once people start to remove observations, what happens is their analysis loses touch or loses its connection with the real world. And then your analysis is worthless. Okay? So that's why I say the data we collect is intended to represent reality, is intended to represent the real world. Based on data describing reality, we build a tool, econometric model, that is intended to show relationships occurring in the real world. But again, if we remove it, we will remove ourselves from reality. And you'd be surprised how often when my team and we were hired to come in and fix something that another consulting team has broken, we would look at the data and it would be like they collected 200 observation, analysis was done on 110. I'm like, what happened to 90 observations? Okay, and they were removed. Okay, so what can we do about liars? Can they be removed? Yes, but it needs to be justified. However, before removing observation, you should ask yourself, why is this observation an outlier? So, to give you an example, I was, as part of my MA thesis, I was building an econometric model that explained house prices. Okay, so you told me how big your house was, how many bedrooms, whether you had a pool or not, blah 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 blah. And based on that, my model predicted houses. Okay, so for example, if we draw it over here, here we had meters squared. Here we had the sales price of a house. Okay, and here we have some relationship. Okay, so here we have some data. Here we have this. And this was my model. Let's assume this is a straight line. This was my model. However, there were some houses over here. Very small square footage, very high price. Larger square footage, but still too high of a price. A very large square footage, big house, still the price was much higher than what was justified by the model. So when these outliers were included, the model actually was somewhere here. And I was sitting there trying to figure out, like, what the heck is up with these houses? Okay, and the answer was these were the houses where celebrities used to live. Okay, so famous singers, famous politicians, famous whatever. This is okay. So now, if I would simply remove them from my study, then of course, green model. But if my model would be applied to a celebrity house, well, in that case, the model wouldn't work. And again, we're not interested in a model that doesn't work. or that works only sometimes, and sometimes it doesn't. We're interested in long-term stable relationships. So what I had to do, I simply introduced a variable, whether a house was a celebrity house or not. Okay, so that's all I wanted to cover with you, because what happens next is econometrics, and I start using Greek a lot. So I highly recommend that you review slides. This is slide 22. So slides from 1 to 22 about econometric modeling. When it comes to the material for the exam for your class is only going to come. And when it comes to this lecture, of course, it's going to come from this lecture slides only from 1 to 22. As I promised, I'm leaving last couple of minutes for any questions anybody might have. So if you have any questions, please let me know. If not, thank you very much. You're free to go. I will see you. Next week. Any questions? Anybody?
No, I guess.
Okay. In that case, have a